Welcome to NASA's VIPER Moon Rover Robot Build Watch Party. My name is Lara Strife, and we're taking you back behind the scenes for an exclusive live look as we're nearing build completion of NASA's first robotic moon rover.
And I'm your co-host, Erica Hengaski, coming to you live from NASA's Ames Research Center in Silicon Valley, California. And today we are with VIPER experts that will be talking more about the mission and, of course, answering your questions from the chat.
We're going to let you introduce yourselves, so why don't you tell us your name and what you do for the VIPER mission. And Antoine, we can start with you.
Thanks, Lara. Hi, everyone. I'm Antoine Tardy. On the operational side of VIPER, I am a rover egress driver. We'll dive a little more into that later. And on the software side of things, I am the lead software developer for science payload integration into rover flight software.
Hi, I'm DW Wheeler, and I am the lead developer for VIRV. And VIRV is the application that VIPER drivers use to send commands to VIPER on the moon, and I'm also one of the VIPER drivers.
Awesome. Well, tell us what VIPER stands for and what are the mission priorities?
Yeah, VIPER stands for Volatiles Investigating Polar Exploration Rover, and the main goals of VIPER are to characterize the volatiles, that is the water, in the south pole of the moon, where we also have a drill so we can characterize depth as well as in different areas on the moon. And VIPER is going to find out if there's enough water there to use as a resource for future missions.
Yeah, water is really important and is one of the volatiles that we're really looking for. Because on one end, for life support, water is drinkable for astronauts and can be broken down into oxygen in terms of life support. It also will enable exploration to go further, since water can be broken down into hydrogen and oxygen, from which you can actually make rocket fuel. And if we were able to launch rockets from the moon, you can imagine that with the gravity that's about a sixth of the Earth, you need a lot less fuel to extract from that gravity well, and you have a lot more fuel that you can use towards, exploring either further or faster.
It's super exciting, and we're really, really excited to get to look back in on our rover at the clean room at NASA's Johnson Space Center in Houston, Texas. We know that the rover is now over 80% complete, so what can you tell us about what's been accomplished so far?
So yeah, if we will get a feed of the rover soon in the clean room, but there we go. So you can see now this is the SITIF, the clean room at Johnson Space Center in Houston, where the SINT team, the Systems Integration and Testing team, is currently building the rover. As you can see, as they told us fairly recently, it's about 80% built. So the feed is now in the clean room. It's built in a clean room because we need to make sure that we don't add contaminants to the rover, or FOD as we call it in the space world. This is for foreign object or debris. You can see in the middle of your feed, there is the rover there. They very recently installed the solar panels. That's the big dark plate at the center of your screen. You can see the SINT team members in there. They are building and verifying that everything is up to plans. The white section that you see on top is going to be the heat spreader, the radiator that will expel extra heat back into space. And all the white sections that you can see at the very top, this is the mast with two gimbals. The gimbals, we'll talk probably a little more about them later, but they're all wrapped in MLI, the multi-layer insulation, to make sure that the rover doesn't get either too cold or too warm.
Now, Antoine, you were mentioning to us that you have been to the clean room. What was your experience like?
The clean room is really cool.
Yeah.
Yeah. SINT set up a really cool setup in there. You can see that everyone has the garbs on. This is for ESD protection, and also making sure that we don't contaminate the rover with hair and stuff like that. You can actually see that all the team members at the moment are connected via a bracelet to the wall. This is also to make sure that everything is grounded. So of course, when I was in there, I had to do the same thing. But getting to see the actual rover being built, you know, we've worked on prototypes a lot, and we've worked on software a lot, and simulations a lot. But getting there and seeing the real thing, and you know, this exact rover is the one that's going to go to the moon. Yeah, that was really exciting.
Oh, awesome.
Yeah, what has it been like for you, DW, watching this rover come together that you mentioned you're both going to be rover drivers, so you're eventually going to be kind of directing this thing on the moon?
Yeah, it's also really exciting. I've been tuning into the feed now and then, and it's cool to me, yeah, like Antoine said, to see the actual article that's going to go to the moon. I've spent a lot of time with simulations and computer models of what the rover looks like, and so it's really neat to see it with the MLI on it, and it looks so clean and white, and the solar panels, and yeah, it makes it easy to get excited about it.
I agree. It's definitely starting to look like the models that we've seen. We have one on our tabletop here in front of us. With the solar panels on there, the mast you were mentioning, which is kind of like VIPER's face, which I think is kind of the further side of the clean room feed. It's really starting to look like the rover, and that's super exciting.
Yeah, definitely exciting. And let's take some questions from our viewers. I know for those that are just joining us, this is a great time to add your comments or questions for our experts.
Yeah, we've already been getting some really great comments. People are saying it's a beauty, which I totally agree. So one of the questions we got is, how long has it taken to engineer and build VIPER?
This is one of those, it depends on how you count. I think our science principal investigator has been working towards this mission for like 10 years, planning it. This mission has gone through various iterations before it was started as VIPER. Not even sure when that happened, maybe 2018. Antoine and I have been working on the mission since 2019. So that's
yeah. And from an actual hardware perspective, it's also a hard question to answer, right? Because I mean, the assembly that you see right now in the clean room has started a while back, but even before that, all the subsystems, you know, the motor controllers, the wheel modules, the solar panels, the instruments, all these were built by different teams or sub-teams that were, you know, going towards that integration, get things together, get it checked out, really tested at the very low level, make sure that everything works before it gets delivered to SINT. And once SINT has all these things together, this is really where, you know, the rover final assembly starts. So it's overall a very hard question to answer from like an actual date, but it's been going on for years.
Well, we have another question here. What are the biggest differences between Martian rovers and lunar rovers?
You want to start with that?
I'll start. Moon and Mars are extremely different. Like it starts from the bodies themselves. Moon is very close, lower gravity than Mars, no atmosphere. Mars is very far away. Oh, sorry, I need to interrupt this because on the feed right now, they are removing some sort of cover. I'm not exactly sure what is being removed right now, but what I heard is that this was partially a solar panel fit check, and so it is possible that those solar panels might also come off either during the feed or maybe later. Once all the checks are done and once the team is happy, if they still have stuff to do inside, because hidden inside those solar panels is all the avionics and a lot of important stuff about the robot. Sorry,
Absolutely. No, yeah, I mean, you're so right, and we should definitely always talk about the feed when it's going on, because, yeah, you mentioned things are coming off, going back on. That's really normal in order to do testing and make sure that everything is working well together. But yeah, to bring us back, I know that the design of the solar panels is also one of those things that's specific to the moon. So you were mentioning the different environments of those celestial bodies.
True. So yeah, the bodies make a big difference. As I was saying, Moon, close, low gravity, no atmosphere. Mars, far away, some atmosphere, higher gravity. And so Operationally, there's a huge difference in terms of time of flight for the data. I'm going to let DW talk
Yeah, I want to talk about that.
because she's definitely an expert in those domains. But it also means that in terms of the hardware itself, it's very different. One big thing, for example, is that since there's no atmosphere where we're going, thermal management is very hard. You like basically imagine yourself where there's no way to expel heat through atmosphere convection. Then basically the rover is sitting on the South Pole, and the left shoulder is smack dab in the sun, really like gets very hot, and the other shoulder is completely in the dark, has no heat coming from the atmosphere whatsoever. And so like the design team, the Struck and Mech team, and all the instruments teams that had to design for that had a really tough job in making sure that the instruments, the components, the subsystems can take those huge thermal differences. That's one of them, for example, from the hardware side, and then maybe operations. You want to take it?
Yeah, this is really exciting for me, especially because I've been focusing more on the operations of VIPER as developing Verve. Because the moon is closer to us than Mars, we can put a lot of the processing that has happened on Mars rovers. We can take sort of the higher brain functions of VIPER and put them on the ground so that they don't need to run on radiation-hardened computers. And so we have a very tight command loop with VIPER, which means that we send it commands about every 5 minutes. And when we send it commands of where to go, we're sending it about 5 meters, like a point about 5 meters in front of it. And if we tell it to run into a rock, it would run into a rock. It does not have hazard avoidance on board the rover. So that's why we need VIPER drivers, so that it doesn't. And that's definitely one of the exciting things for me, is that we're going to be in the loop as the rover is driving on the moon, sending it each couple of steps, giving it new commands. And that's definitely something that you wouldn't be able to do if it was on Mars and there was a 20-minute delay. That's why they send them like sets of commands for a whole day, what they need the rover to do.
Well, that leads me perfectly into this next question, because we're getting an ask about, does the input delay from Earth to the moon matter a lot? And you're saying it's really small in comparison to with Mars, but there is still a slight delay, is that right?
Yeah, it's on the order of like 6 seconds, maybe. A lot of it's just going through the satellite link around the Earth, and so we can't operate it with a joystick. Like it's enough that you wouldn't want to try to joystick it on the moon, but we are close enough that we can send it fairly limited waypoints on a fairly regular basis.
Gotcha.
Awesome. And here we have another question. What is the projected lifespan of this rover?
So we are landing at the South Pole at the very beginning of the quote-unquote South Pole moon summer. So just like if you know about Sweden, you'll know that they will have pretty much 6 months of sun and then 6 months of dark. I'm simplifying. But we're trying to do the same thing here. The South Pole is very interesting for many reasons. Scientists think that there's the highest likelihood of water there, partially because the same reason that we're talking about right now. Since the light is coming because of the position of the sun rays are coming at a very horizontal angle. And so there are like places where there's a lot of sun at all times. There's also those permanently shadowed areas, PSRs. Right. Which we are very interested about. Imagine a crater at the South Pole with some little walls on the side. If the sun rays always come very horizontally, the center bottom section of the crater could be PSR, permanently shadowed region. And so we are going to be basically sending our robot into the dark, into those PSRs. Like those are going to be very critical events in the mission. Because since we're solar powered, we won't have any power once we're in there, so we have to rely on our battery, and be able to go get science there, figure out water distribution, and kind of on the clock, get in, get back out. Very, very interesting in an ops and driving perspective, and for all the science teams.
Awesome.
Yeah, and the summer lasts about 4 months. So we're there for 4 lunar days. A lunar day is about 4 weeks. And so we're going to, an interesting thing about the VIPER operations is that for 2 out of every 4 weeks, the VIPER rover can't talk to Earth because there's no relay satellite. So we'll just have to send VIPER up on a high mountain where there's lots of sun and tell it to hibernate for a while until we can come back and tell it what to do. So they said the VIPER mission, we're planning for about 100 days, but we won't be able to command VIPER to be doing things for 100 days. Some of that's going to be time in our safe haven waiting for the Earth to come back above the horizon so we can talk to it again.
Makes sense. I mean, you keep leading me perfectly into the next question. So we've got another one here. Hi, I'm Miriam. I'm 8 years old from Australia. Hi, Miriam. And she's a big fan. How long does it take for the rover to reach its destination? You just talked a little bit about the time span that we have to work with. Maybe you can unpack that a little bit more also in terms of what its destination is.
It has lots of destinations. So as VIPER is moving on the moon, it has a very specific plan that our planning team has worked out. We said, as Antoine said, we're going to the South Pole. The sun is very low on the horizon. There's lots of long shadows, and the rover moves about the same speed as the shadows, which means that we have to plan very precisely where is the rover going to go so that it doesn't get caught by the shadows. So we have that all planned out, and the scientists have designated particular areas that they're interested in studying very precisely. We call them science stations. So I think we have 4 or 5 science stations during the first lunar day. So the first lunar day we'll land, and then we'll just head straight for those science stations. And we can't be behind schedule because we'll be caught by the shadows, and we can't be ahead of schedule because then the area is still in shadow, and VIPER doesn't operate in shadows. So we've got this very precise timeline to go to the science stations and to dig there, and then we have a specific time when we have to leave each science station and get to the next one. So yeah, VIPER has a lot of places that it wants to go. Right? I can tell you its top speed is 20 centimeters per second, which is about 0.4 miles per hour. And
that's about that fast. Approximately.
That's a great.
It sounds really slow if you're driving a car, but you know, cars drive on roads,
right.
And there's no roads and VIPERs for scientific instruments. So yeah, to do the first lunar day's path, that will take 1 lunar day, like 2 weeks.
And that's
2
quite
weeks
fast for a rover, if I'm not mistaken.
It's like way faster than a lot of the rovers that have been there already.
Yeah, it all really comes from that, the fact that we're quote unquote racing the shadow. The operations, like, from an engineering and operational perspective, present a lot of really cool challenges. As DW said, you know, we land, we egress, so just like get off from the top of the lander onto the moon, and then we basically directly go in between those science station phases and rails phases. So when we drive on rails, which is basically just go from A to B as fast and safe as you can, then really...
But not too fast.
Really the drivers we're really beelining it straight to the next science station. We have like a path that the planners have designed for us to make sure that we stay within, within comms with the Earth mostly, and that we have like good sun. But really, while remaining safe, go as fast to the science station as possible. So we'll go at that full like 20 centimeters per second speed, really blazing fast.
Yeah.
Blazing fast, you know.
Yeah, and then there's a 5-minute cycle for each command. We'll tell it to drive, and it will drive for 5 meters at 20 centimeters per second, and then it has to take pictures, send them down to Earth. The pictures have to be processed. The drivers will look at the images and we'll look at it. So a lot of the time it's not moving at its top speed of 20 centimeters per second.
True. Blazing. And then we get to the science station, of course, and then like all of a sudden the focus shifts, right? I mean, we're kind of rastering the science station itself to figure out, to like leave all the instruments, get a lot of cool data of, we want some XY mapping too, right? So we do kind of a grid pattern to make sure that we get this XY data, and we move a little slower actually in those areas to get more data, and then we get to the drill sites within the science stations where we get that Z information, where the drill is going to start drilling by bites, and we're going to analyze what they found, making sure that, well, basically trying to figure out not only in X and Y, but also Z, how the water is distributed.
Awesome. So we have a question for you, Antoine. Where does a driver sit, smiley face?
So you've probably seen either in movies or in past feeds, the operation centers that NASA usually have. It's in those movies, the rooms with all the screens and all the people sitting there.
Big rooms.
Big rooms. And so the way, part of the way the operations are set up for VIPER, in the main room, front room, we have 2 rows. The front row has the driver sitting in the middle. Then you got co-driver, real-time science, and navigation. They all form the drive team. And then on the front row, there's also the science lead that's going to be there. And then behind us, kind of in a supervisory, they can see everything we do, right? We're like really the real-time driving ops part. And then behind us, there's the flight director, the commanding station, the system station, the mission. What's the name of the mission?
Mission director, I think.
Mission director, something like that. Sitting back there too.
Important people.
People that can look over our shoulders. It's set up that way so that they can really see what we're doing. We don't have to. We don't have to know exactly what they're doing at all times. They'll do stuff in the background in terms of updating data, making sure that the telemetry rates are fine. But if they need to interrupt us, they will tell us. And we mostly do our thing in the phases that we know, specifically rails and science stations.
But I think it's cool how we have the drive team set up. It's not something that's been done for previous NASA rovers because we have to do this in real time and send commands so often. We have to make sure that we're all there and that we're ready to analyze the data as soon as it comes in. So when we talked about having a driver and a co-driver, there's 10 people who are trained as drivers for VIPER, and we will all take turns cycling through. We'll come on shift as a co-driver, and then we'll become drivers. So that's all the same group of people with all the same training. So that also helps that we'll be able to step in for each other at the same time because we have these time constraints. During those 2 weeks that we're commanding VIPER, we will be operating around the clock. And so we will always need to have somebody at those stations and those consoles. And then I also think it's really cool that we have a real-time science who's sitting right next to the driver. They're looking at the science data that's coming in as it's coming in. They're interfacing with the science team in the back room, and they can tell the driver, hey, that looks interesting. I know we planned to do this raster pattern, but actually let's go over here because this rock is super scientifically important. And then we're even planning, each science station has 3 drill sites planned, but we are planning to change the 3rd drill site depending on what we find. So as we enter the science station and start getting data, the science team's going to be in the back room in real time debating where should we tell them to go, and then planning is going to put together a new plan, send it to us as drivers, and that's all happening within the time that we're in the science station. And planning is still keeping in mind, we call it the bingo time of when we need to be exiting the science station so that we can make sure that we have enough time to get to the safe haven so that the rover stays in the sunlight.
Again, you're leading me so beautifully into another question. Jared Lemon is asking, are there any plans to operate it during lunar night?
No. It's a solar-powered rover. It can only survive 50 hours in the night. And I think our biggest problem is that we don't have comms with it during the night. So even if we built a rover that would survive the lunar night, we couldn't talk to it.
So it's a creature of the day. That makes sense. And we had another question that kind of relates to that. Mark Bass was asking, how long can the battery last without the help of the solar panels?
Yeah, 48 hours.
48 hours, wow. Okay,
Yeah, and that's when it's in hibernation mode.
got it. Not doing too much activity, not racing at its top speed.
Exactly.
Yes.
Cool. Another related question, Bojack Cates is asking, how long does it take to charge the rover?
I don't know exactly what like the.
It's kind of charging constantly.
Yeah,
Sounds
we
very
like
fun.
this is actually another one of those very varied constraints that really make the driving part of this so interesting. Is that as we drive, we charge, and there's solar panels only on 3 sides of the robot.
Yeah, exactly.
So as you,
Yes,
as you can see out here,
the front side does not have solar panels.
and so
And the sun is so low on the horizon that it's always coming from like a horizontal direction. So as we're driving, the optimal way for us to be pointing is for an aft corner to be pointing towards the sun, which means depending on where we want to go, we might have to drive backwards.
which
Oh.
the mobility platform actually lets us do fairly well. Since we have to keep the sun in consideration, we often have to drive backwards or sideways crabbing, as we call it. The mobility setup of this robot is not the same as say your car. I mean, yes, it has 4 wheels, but if you see here, each wheel actually has its own steering motor, which lets us do crabbing. Which basically, you can move forwards and backwards, but you can also move, at 45 degrees sideways in those like crabbing situations, which enables us to respect more of the constraints that we get from, sun, comms, science, thermal. There's a lot of them, and this is a lot of work on the ops team to figure out exactly how we want to drive it.
You also brought a wheel from the McGrew model. Tell us a little bit about it.
Sure, I'm very excited about this one. So this wheel was actually taken off for this show off of the McGrew prototype. It's our mobility prototype, really, that we use for making sure that the robot can actually do what it does.
Moon gravity relevant unit, right?
Yes, exactly. Exactly, you got it. Yeah, I rehearsed it, but I wasn't sure if I was going to put it in.
You can't say McGrew without saying what it stands for.
Fair enough. So that unit is basically the same mobility platform. So same suspension,
Looks a lot like
same
this.
steering, and same wheels, and everything else was kind of removed and put off board, so that the platform itself could be 1/6 of the mass of the VIPER rover, which means approximately equivalent weight on Earth. That all being said, this wheel right here is not the lightweight version. This is very, very close from what's actually going to go on the rover. You can see on the feed, their wheels are not mounted yet, but they will look very, very similar to this. They are very, very lightweight if you want to actually try it. The Struck and Meg team did an amazing job with those. You can see actual spokes. Those are actually very similar to bike wheel spokes. Don't reinvent the wheel. Quite literally. Bike wheels need to be very light and very sturdy.
Yeah.
These need to be very light and very sturdy. Of course, for space systems, the lighter you are, the less fuel you use, and the more of your allocated mass you can use for the payloads, the science instruments. So had to be very, very light and very sturdy. We have some inserts on the grousers to make sure that it doesn't get too much damage, wear and tear as it goes. And it's as a big diameter as we could, because you can imagine as it rolls over some type of obstacle, the bigger the wheel, the more we can actually jump on top of well, not jump, but roll on top of an obstacle and then go back down on the other side. So.
And it has encoding on.
Oh yes. Do you want to talk about the encoding real quick?
Oh, I thought you were gonna. So we have this pattern around here. So 1/4 is all black, one is half black, half white, one is half white, half black, and then, or not white, silver. And so we have cameras on each wheel. So there's one camera for each of the 4 wheels that takes a picture outward through the wheel, and so it can show this pattern, and that means that when we take the picture and then we command the rover to move forward, then we can take another picture and compare the pattern on the outside and tell how far it moved.
Yeah.
Very cool.
This wheel actually has a lot of wear and tear. You probably cannot see it, but it has a lot of wear and tear because it's been on the prototype for so long, and we've done a lot of mobility testing with it, basically on Earth, but in controlled environments, trying to make sure that we can actually meet our requirements in terms of going on top of rocks, slopes, craters. Actually, a good time to bring in the multi-center part of this project. So NASA Ames here is doing the software, the mission systems engineering, the direction of the project, and the project management is stationed here. But as you see on the feed, the SINT team and the hardware integration and a lot of the design teams are based in Houston, Johnson Space Center, and then a lot of the mobility testing that we did was at Glenn Research Center in Ohio, where we were basically able to use their facilities to characterize how well the robot does in slope environments, crater environments, rock environments.
And that was a super fun test. All the drivers got to go there for one day. I mean, Antoine was working there for weeks doing these tests, but so some of the drivers, like me, have more of a software background, and some of them have more of a hardware background, which is a really great synergy because we're able to learn from each other. So one of the best parts of the project so far for me was going to Slope Lab, where they have this basically a gigantic sandbox that can tip up and back down, and then we can see how does VIPER do at different slopes at 10 degrees, at 15 degrees, with different size craters and rocks, and that was super fun for me to see.
Very cool.
Mapping in our heads the two different worlds. We work a lot in simulation to make, to practice operations and all that kind of stuff. And then some of us also worked a lot on the hardware side because we had to prove that, as designed, it will work. Having those two words get together within the ops team, exchanging all the information, exchanging the knowledge, so we really all get to a similar understanding as it goes through. That part has been really exciting too.
Yeah, that was really good. Also at the Slope Lab, because I work on Verve, which is the driver application. Some people have compared it to a video game where you sort of see the terrain of the moon from a satellite reconstruction, and then there's a little model of the rover, and we can click on the terrain and say, okay, rover, that's where we want you to go. But we're so zoomed out, right? So when we send it 5 meters at a time, or it can see 15 or 20 meters out, we look at this whole big map and we're like, oh, it's such a little rover. Why can't you do more? Why can't you see more? Why can't you go farther? That's not very far to go 6 meters. And then to actually be in the Slope Lab and have McGrew there and be like, 5 meters is over there. Yeah, that's kind of far. Maybe you wouldn't want to send your rover 15 meters when it doesn't have any hazard avoidance on it. So that was really cool for me to see the hardware in action.
Absolutely. And I like what you said about the other centers being involved. I know we also have a science instrument from Kennedy Space Center. We've got scientists at Goddard Space Flight Center. So NASA folks all over the United States are working on this mission. Before we go too far from the wheels, someone did ask in the chat, what are the wheels made of? I want to find out myself.
Aluminum.
Aluminum.
Aluminum, yes. The grousers are actually harder anodized to make sure that we have there's less wear and tear on them, and the grousers are stainless steel.
Okay. Is that what the rest of our rover is made of as well, or?
It's a very large mix of components. A lot of aluminum there for sure.
Okay, very lightweight.
Yes.
And like you mentioned, you guys have been practicing driving. The first little bit of driving of the rover will be going down the lander onto the lunar surface. Tell us a little bit about that experience and how that's going to work.
I'm very excited about this one.
Yeah.
So this is the phase of the mission that's called egress. So basically the lander lands on the surface of the moon. We're still on top of the deck. We are tied to the lander. The ops team will do all their checkouts. We've landed, we've been shaking really hard, so they do all their checkouts, spin all the wheels, release the launch logs, all make sure everything is okay. Right? And once that's done, in parallel, there's the first part of the egress driver team is deciding which way we're going to go and how we're going to egress that. And as soon as we get...
Because there's 2 sets of ramps. Right. You can go down the front or the back of the lander.
Exactly. And so once we get the green light from the rover team, hey, everything is good, you go for egress. Then there's four of the 10 drivers are trained as egress drivers, and so we, in collaboration with the rest of the team, also will basically stand up. So since all those suspensions are separately actuated, we basically, from the stowed position, will stand up on top of the deck, which will, finalize the release from the lander, and from there on, we're on our own. No more lander power, no more lander communication. We are now our own rover, and from that stood up position, we have to drive down the ramps. They're pretty steep, 15 degrees at nominal, and then back onto the surface until we can say VIPER itself is on the moon. It's obviously a critical part of the mission. It's pretty scary, of course, because those ramps are very steep, and you have the whole team waiting behind you to go do their science. Or
ramps could land in a crater and become even steeper. We don't know.
There's a big component of really be careful with that one, because everything else needs to happen, which makes it kind of scary, but also very exciting. Really being able to enable that phase and just get to the point where we're on the moon, VIPER's on the moon, hand over to the next shift, and I'm very, very excited for egress.
Yeah, it's definitely going to be, I think, nerve-wracking to see what orientation we end up landing in and then getting it on the moon. And then it sounds like, DW, does your driving job kind of start once Antoine and the rest of the egress drivers have gotten it on the lunar surface?
Yeah, I'll be driving it once it's on the moon. then the rest of the drivers will also take turns driving.
That sounds really exciting and also stressful. I don't know if I would want to be behind the metaphorical wheel, but you guys are experts, and I can't wait to see it all come together.
That's the cool thing about the practice, right? I mean, we test so much and we drive so much. I mean, McGrew, we have now nearly 20 kilometers on the platform going, and we do some of those egress tests that you've probably seen features in NASA recently about those. So, yes, it is a scary moment. Yes, it is an important moment. But this is also why we test, right? And we design, analyze, test until we get the confidence that, yes, we're ready to do this. We're ready to do this right. We have developed the procedures and the operations to do it as right and as safe as possible, and really get to the point where it is scary, but we know we can do it.
Well, at some point, I would have to say one of the parts that I like most about working at NASA is that being in meetings and having people be like, we don't know what the surface of the moon's going to be like because we've never been there before. And that's always super exciting for me, is that we've trained as well as we can. We have these amazing simulations, and we've talked to experts from different parts of NASA. But at the end of the day, no NASA rover has been to the South Pole of the moon, and it's all going to be discovery and exploration.
Yeah, you'll be the first. That's very exciting.
Yeah.
And Antoine, does your job driving end once you're on the lunar surface, or you'll continue driving? You can do the flat as well?
I can do the flat as well.
Okay.
It's likely not going to be as flat as we would want it to, but yes, the 4 egress drivers are also drivers once we're on surface.
We definitely need all of the trained drivers as we're working around the clock.
Yeah, the operations cycle is going to be fast, but we have a great team, overall ops and drive team, and the drivers with coming from within the project with a lot of different expertises, and really once we get into those sims and we start melting all those experiences together and really learning off of each other, that's really where the magic happens.
Yeah.
I can't believe I'm saying that we're already about halfway through our stream, and we're so grateful to have you both with us. I know we have 2 more VIPER mission team members who are going to join us in a little bit, but before we send you on your way, we do want to know sort of what are you most excited about for the VIPER mission?
Me first? I'm really excited about seeing the pictures that come from VIPER. As a driver, when I'm on console, I'll be one of the first to see the pictures from the moon, and I can't wait.
repeating myself, but the egress bit is the part that I'm very, very excited about. I worked a lot on the mobility, on the gimbal side, making sure that everything, that we have our antenna tracking the Earth at all time, and that the process of driving down is correct. As DW said, we've tested so much, designed so much, iterated so much, and then there's this special NASA thing where at some point you got to do it, and you can do it only once. It's really part of the beauty of it, and I'm extremely excited for this.
So are we, and so are a lot of people in the chat. We're getting a ton of really great comments. What an awesome job. Wow. I mean, I totally agree with them. Thank you so much both for being here. We're going to show just our live clean room footage for a little bit while we bring out our other VIPER mission team members, but thank you again. You've been amazing. So many good answers to the questions. So.
Yeah, thank you. We had a lot of fun with you too.
Yeah, thanks for having us. It was great to have this opportunity.
Thanks, yeah, it was really cool.
For those who are just joining us, this is NASA's VIPER Moon Rover Robot Build Watch Party. We're seeing live views of our Moon Rover as it's being built in the clean room at NASA's Johnson Space Center in Houston, Texas. If you'd like to send your name to the moon with VIPER, you can go to www.nasa.gov/sendyournamewithviper. Submitting your name there will generate a custom boarding pass, and your name will be added to a microchip that will fly aboard VIPER and land with our rover near the lunar South Pole.
Somehow.
Mike's up. Bring him down.
Right. Welcome. Thank you for joining our watch party. And we are coming to you live from our studio here at NASA's Ames Research Center in Silicon Valley, California. We'd love to have you introduce yourselves. If you could tell us your name and what you do for the VIPER mission. We can start, right?
Yeah, sure. So my name is Andrzej Jackowski. I am the one of the main engineers on the motor controllers, which are the electronics that make the rover move. So the entire mobility system, so it makes the wheels move, makes the steering move, makes the suspension move, and it also is responsible for making sure the eyes and lights of the rover are capable of moving around so we can see what we're doing, and making sure that we're able to communicate with the Earth. So the antenna at the top actually moves around and has to be pointed at the Earth the entire time, and the electronics that I was developing are part of that. And furthermore, I'm also one of the rover drivers, which
super cool. We're so happy to have so many rover drivers with us today. I know we've got another one right next to you.
Hi there, I'm Jasper Wolfe. I am not one of the rover drivers. I have a different operational role, which I'll talk about in a moment. So my development role is on the mission system side of things. So I'm a systems engineer there. I work with mission operations and the ground data system. And then for operations, I'll be one of the systems positions. And so there we look at the health and status of the vehicle, making sure that we're actually have a functioning vehicle to do what we need to do. And if there's a problem that is coming up, we need to work very quickly to get it solved, and then maybe even bring in the anomaly response teams to help solve that quickly.
Awesome. So Jasper, for the folks that are just joining us, can you tell us a little bit about what we're seeing here at the VIPER Clean Room?
Yeah, so today looks like we're about 80% built. I think that was the report from this morning. We have the solar panels installed. That's fairly recent. And you can see the solar panels in the center there. That's the big black object in the middle. They are, let's see what else is going on. We've got the mast installed. On the mast we have the high gain antenna. So the high gain antenna is our primary means for communicating to Earth. We get our high data rates through there, as opposed to something in, say, safe mode where we need to go down to a low gain antenna where we have more of an omnidirectional capability to get communication that way. So that high gain antenna is sitting up the top. And then a little further down we have the nav lights also on that mast. The nav lights and the nav cams, and so they're our primary eyes of the vehicle that Andre was just talking about.
Yeah, I mean, can you tell us a little bit more about sort of the size, the shape, why the rover looks the way it looks?
Yeah, sure. So the size is about 1.5 meters by 1.5 meters. What I've been told is about the size of a golf cart, and you can kind of get a decent idea of how big it is, like with some of the engineers around standing around it, to see how like it kind of scales with a human. And the thing that also a lot of people ask about, and you can kind of see it with immediately, is that it has this very box-like shape.
Yes.
And the reason for that has a lot to do with the environment that we are going to be in. So it's been said already, and repeating again, I might as well, that we are going to the South Pole of the Moon. And since we're on the South Pole, the sun is actually going to be coming on the side. Right? So this is actually opposite situation that a lot of people have seen in other rovers. So a lot of people think about the Mars exploration rovers, Spirit and Opportunity. They actually have their solar panels at the top. So we actually want them on the side because since the sun is coming sideways, we want to catch up as much of the sun as possible, and then that gives us the most amount of energy and the most amount of power, so we can keep doing what we need to be doing. And if you want me to continue, that's also why the radiators, which is the white parts that you see at the top, that's actually how we reject excessive heat from the rover. And since the sun is not there, like it would be normally if you were closer to the equator, that's just the deep blackness of space. So all that heat is just that we don't need. It's just being rejected that way. So it gives this rover this very box-like shape, but like all things that we do it for a purpose. And that all drives design. It drives drives the engineering challenge, and it's the environment that drives the engineering challenges that we find different ways to solve.
Exactly. Okay. So it's not just for aesthetics. We didn't decide we thought that a boxy rover was the best look. It's got a function. There's a reason behind it. It also looks good, though, if I do say so.
Oh yeah.
I like the look of it.
It's definitely
It's definitely
like stands out given in all the lines of rovers.
And we see the mast up there. What is the function of the mast?
So the mast is where the high gain antenna and those cameras are, and that also is a part of the design decisions around having a relatively tall structure there. Is we want the high gain antenna to sit quite far off the ground so that we get away from a lot of the multipath and have a much better line of sight back to Earth for communications. And then similarly with the nav cameras sitting up the top there, we want to be able to actually see in front of us, and if we had quite low cameras, we wouldn't be able to see behind obstacles. And so having those quite high allows a much better field of view, and we can discern our obstacles in front of us a lot more easily.
Gotcha. And how do we kind of like test this rover if we're not able to drive it out on Earth anywhere because it's too heavy, right, or too big?
So it's not too heavy per se, although but it's designed for the weight that it needs to be. So as many people know, the moon has 1/6 the gravity of Earth. So that means this thing is going to weigh 1/6 the weight that it is on Earth on the moon. So as a result, we want to actually take advantage of that. So as a result, we designed this for the moon's environment. We do as I said, we do everything for a reason. So this actually allows us to put in more payloads, more science, and more capabilities that we otherwise wouldn't be able to do if we made the structure strong enough to handle to be able to want to operate on Earth. But that, as you said, that actually does introduce other engineering challenges. So it becomes very difficult to test because this thing is not designed to operate on the Earth gravity. So to get around that, it was mentioned in the earlier half, but I'll repeat it, that we built this prototype unit called MGRU, which I believe stands for Moon Gravity Representative Unit. And what that is that we took out pieces of the rover, or offloaded as much as we could, such that the weight of the mass of this platform is 1/6 the mass of the actual rover. So meaning that it weighs the same on Earth that the real one's going to weigh on the moon. So now you can try to drive that, and you can expose it to the correct driving conditions, and it's going to be seeing the same forces and the same dynamics that the real one's going to be seeing. So you have to come up with new ways, very clever ways to try to work around those problems.
Right. Okay.
It actually looks a little bit like this.
Right. Yeah.
It's a lightweight version.
Yeah.
And that's where this wheel came from as well. So
Yes.
that has proof that we have been doing some testing here on Earth, but not with obviously our flight unit, with something a little bit less massive. We can jump into some of our audience questions because we have a ton. If you guys are game, if you're ready for it.
Love to hear
Let's
it.
do it.
If you have questions for our experts, please don't hesitate to put them in the chat. We'll do our best to get to as many as possible. One question I have right in front of me is, how does the team determine where to drill and the reasons for those locations? What sort of age will these ice deposits range from? That's a tough question.
I can take part of that.
Please do.
So in determining how we drill, where we're going to drill on the moon, I'll kind of start back a little bit about the traverse plan and talk about that, and then we'll get to the specifics of drilling. So we start with a lunar map of the south pole of the moon, and we have a relatively high resolution map there. From there, that goes to the science community to understand the ice stability models that could be there as a function of the terrain conditions. And from that, then they designate these areas that are of scientific interest, and these are the science stations. Within the science stations, then, depending on the local terrain conditions, they pick out certain drill sites, and then we have 3 planned ones. So we want to have a plan going in so that we have something to execute against. And as we go along there and we take the first drill, we'll learn a lot. And then we'll take the second drill, we'll learn a lot more. And by the time we get to the third one, while this is happening, there's a full real-time analysis going on at the same time that discusses and prioritizes how we could change that third drill site. And it's a really amazing process in the science community there in the Mission Science Center that does this whole process and reselects the third drill site, which is actually going to be based on what we're learning real time. So that's the where we drill side of things. The other question is probably best answered by one of the science members.
Yeah, I know that we've heard from some of the science team members that some of that ice deposit might not have seen the sun for millions, billions of years. So it's exciting also as part of the mission, I think, to see what we find. We'll learn a lot of that as we go.
Yeah, and that has to do a lot with the permanently shadowed regions on the moon.
Right.
So as I mentioned earlier, that the sun is very low in the horizon on the South Pole. So since it's coming sideways, actually you can kind of demonstrate it here. That you have this grouser here, and it's acting, and we have craters. So and there's craters deep enough that the sun actually never reaches the bottom of the crater because it's so low in the horizon.
Right.
And as a result, I believe it's from comets hitting the moon, and because these areas don't see sun, the ice never evaporates. So that's actually how, to my understanding, that's how it actually ended up getting deposited over so many years.
That's my understanding as well.
We have another question. How will the rover communicate with VIPER team?
Oh, communicating with VIPER team. So that the primary communication that we'll use starts with the high gain antenna on top of the vehicle. So that's the big mast sitting at the top there. There's actually a low gain one just above that as well, but we generally use the high gain for more communications. That signal then goes straight to Earth. So we do not have any relay satellite in the link there. It goes straight to Earth, to the DSN station. So there are 3 sites around the world, Madrid, Canberra, and Goldstone. And so we'll communicate to those Earth stations. That then gets funneled back to here at Ames. We have the Mission Operations Center here at Ames, and then it gets distributed out to our other parts that are also performing operations, so to Kennedy Space Center and to Johnson Space Center.
And what's the delay between?
The delay round trip is a few seconds, which actually ends up defining a lot of how we conduct our operations. So we are in a position where we're not, we are unlike the Mars missions where it's quite a long delay and they have to pre-plan and uplink activities for it to execute by itself. And we're not close enough to really just sit there and joysticking it, I think is the term that people like to use. So we can waypoint drive, and that few seconds delay there really governs the style of operations that we can actually perform.
Got it. And I know we talked a little bit about the mass of the rover and how it relates to lunar gravity, but there's a question here: how heavy is the VIPER payload, and what kind of rocket will be used to bring it to the moon?
Okay. So the payload that actually ends up being two questions actually.
It sounds a bit like two questions.
Because the mass of the payload itself actually includes this piece called the rover release mechanism, which is a ring that's kind of like a triangular ring almost that sits on the bottom of the rover, and that's actually going to be bolted onto the astrobotic lander that we're going to be using. And that piece, and that's actually what's holding us down and allows. And once we land on the moon, that's actually going to be releasing us, and then we can drive off the lander. So it ends up being actually two questions there. To my understanding, the entire system together, I believe it's around 490 kilograms, but unfortunately I'm going to need to be fact checked on that one. But to answer the rocket, we are going to be landing on we're going to be launched on a Falcon Heavy from SpaceX, and in turn we're going to be on top of a astrobotic Griffin lander for the mission.
That's right. Okay.
We have another question here. How long will one person drive a rover?
Ooh, that's a good question. So it's actually split up into two shifts. The entire on one in total the entire mission, but for a single but then to bring it to shifts, what's going to happen is that there's actually two roles and two people driving at this always. A driver, which is the person who's actually going to be sending the commands, and a co-driver, and that person is going to be interfacing with the other flight operators, having a very mission awareness, and also confirming the commands that the driver is sending. And also, it's also a redundancy, because if something happens, because anything could happen, you have to be prepared. Let's say for some reason something happens to the driver's computer, right? Probably not going to happen, but if something happens, you at least have that ability to then take over, because they have the exact same tools, the exact same commanding, to be able to take over and send commands, so we don't lose any mission tempo. So how it works is that a driver will first come in and they'll sit in the co-driver seat for 4 hours, and then they will actually swap to the driver position, and then a new person will come in and take the co-driver, and then that keeps rotating for as long as for as long as we're driving for that duration.
Wow. And we said that's about like a 2-week span of driving?
Yes, to my understanding, it's about 2 weeks of continuous operation, and then we go to these areas called safe havens, which are areas that we're going to be receiving a little bit as much sunlight as possible, while the Earth is going to fall under the horizon. And unfortunately, because we require line of sight, we won't be able to communicate the rover, so it kind of goes to sleep for 2 weeks.
Right, that brings me to this question. What happens if the robot is lost in the shadows? So I'm assuming we're going to do everything in our power not to lose the rover, but what if it's in a shadow?
Okay, well, for starters, a lot of the design for the rover, once again, we do everything for a reason, is making sure we don't end up in that situation. So this is the second fastest robotic rover ever designed. The fastest robotic one being the Russian Lunokhod. And the reason that we do this is actually we're trying to race the shadow the entire time. So as we operate in what I like to call the local South Pole summer, where you know how in the Arctic Circle or Russia or North Sweden you have very short nights. That we're taking advantage of that because we're a solar powered rover. So as the time goes on, we're not going to have those summers, so we have to make sure we're ahead of the shadow. because if we get caught, if we do have the ability to hibernate, which the rover will lock down all its systems, turn off everything it doesn't need, and try to keep everything as warm as possible. But if we get stuck in an extended period, that could unfortunately end the mission, which we do everything we can to make sure we do not end up in that situation.
And just to add to that, when we talk about shadows, there are really two types of shadows that we consider for the mission. There's the sun shadows that is all to do with power generation and our ability to stay warm, which is also something that we want to ignore at some point and actually go into a shadow and do these permanently shadowed regions.
Yes.
And then we have our communication shadows. So we are a direct-to-Earth communication mission, so we need to have this comm line of sight at all times. Except for this safe haven period where we purposefully go into a hibernation state. And so we have a really complex situation where this terrain that we're going through has both sun shadows and communication shadows, and we're trying to outrun both. And so you get this really narrow kind of window of opportunity to actually to traverse through.
Wow. Let's see. Here's a good question. What's the maximum slope the rover is designed to handle?
So in terms of mission of what we actually plan to do, my understanding is 15 degrees. However, it is actually capable of doing more, and it's one of the, some of the fun things that we're actually not that we're actually going to do it, but we have tested it to extreme conditions past what really our requirements. And it's one of those things that we could actually use the unique suspension that we have developed to be able to handle. So this model kind of shows it. The suspension arms and each of the wheels are able to go up and down. And what we could actually do is that when we're going up a steep cliff, we could actually cause the rover to lean into the slope to be able to handle steeper slopes than if we had a more traditional fixed suspension. But to answer the question, 15 degrees.
Okay, but we're prepared to kind of adjust as needed.
Yeah, so the idea also, the drivers try to avoid trying to do these more extreme slopes if possible, which actually goes into one of the really cool features of the rover. Sorry if I'm rambling. Which is the fact that since we have two cameras, we can do what's called a stereo vision image. So we have two cameras, same way we have two eyes, and doing a lot of complicated math that I don't understand, we're actually able to get what's called a depth of field and generate what's called a point cloud. So we could actually scan the area around us and generate these things called hazard maps. So what ends up happening is that the views that we see as drivers end up turning green to red, saying red, you can't go there, green, yeah, you can definitely go there and no problem. So it ends up being a really cool system.
Very cool. I mean, you guys are doing such a good job of leading me into the next question, and I so appreciate it. We got this question in the chat. I have a question about what kind of cameras are on the rover and what are they for? So you just started touching on that a little bit.
Okay. Yeah, so we have 4 cameras at the bottom that look at each wheel. So I don't really have a good example to show, but they're kind of tucked in on top. They're kind of tucked in under on top of each wheel, and they're looking at the wheel itself. So that allows us to see if there's any obstacles or hazards that are right next to the wheel, and see that there's anything that we need to be careful about. And then there are 2 cameras in the front as part of what I call the navigation gimbal. That's part of what my system, the gimbal controllers, has to move. And those are pretty much the driver's eyes. And those we can point those cameras wherever we want in a mostly 300. We can point them wherever we want, but there are some obstructions such as the chimney cap, and those are things we have to work around, and those are going to be the driver's eyes when driving mostly in a forward direction. And we actually have aft cameras, which you can actually see that those 2 kind of gold-looking squares inside that you can see in the back of the solar panel. Those are 2 cameras right there that do the same stereo imaging that I mentioned earlier. So we could see what's going on when we try to drive backwards.
Awesome. And one viewer here is asking, what's the best thing about working for NASA?
There are a lot of cool things about working for NASA. I mean, being involved in any kind of mission here means that you're being on the bleeding edge of something that's just, groundbreaking. It's exploration. It's awe-inspiring every day. It's also just fun to work with the kind of people that we get here. We have such a diverse and great group of people. Everyone's just really excited to be a part of this, and coming to work and getting to work with these people. It's just, really gives you energy every day to see everyone around you all focused on this great mission.
Absolutely. How about you?
That I was told I get to drive this thing. Yeah, I mean, yeah, you pretty much covered it.
Awesome.
Yeah. We also got a question about the clean room. I think we might have touched on this a little bit earlier, but can you tell us a little bit about the garb that people are wearing and these links that they have on their wrists?
Yeah, sure. Yes, I definitely know a lot about that. So the garb they're wearing, so first, well, I'll start from top down. First is the hairnets. That is so we don't want like particulates or like any like fibers or anything coming off people to end up on this rover. We call that foreign object debris, or FOD. So just trying to keep that in, making sure that nothing like unexpected ends up and causing problems. So you want to, when it comes to engineering, designing, and building these things, you want to know exactly what you have and what you're flying, and unknowns really muddle things up. The garb itself is actually a special garb called that's for ESD, or electrostatic discharge. So if you've ever touched a doorknob and or rubbed your feet on a carpet and touched a doorknob and shocked yourself,
Oh, yeah.
that is actually really dangerous for electronics. So if that happens to any of our electronics, there is a real chance you can destroy them. And obviously, we're not in the business of breaking stuff, so we do all we can to make sure that doesn't happen. So that actually allows it to discharge and you not build up that static electricity. And that's actually also what the wristbands are for. So that actually, if you build up any charge from just moving around, because it just happens just by moving, by putting that wristband on, you're grounding yourself. So you're discharging all that excess static electricity, so this can't happen. And then the last thing is the booties and gloves. The same deal, just making sure that everything's clean and you're not tracking dirt anywhere.
And another question here, what are some of the challenges that the VIPER team faces in assembling and testing the rover? I know there's many, but if you can just give us an example.
There's a whole host of challenges that happen there. I mean, in any kind of integration effort, when you're bringing individual pieces together for the first time, there's going to be some kind of problem that comes up. And when you have such a complicated system with so many individual pieces that are all feeding together, and in such a constrained space as well, with the design of the rover and how it has to fit together to form its operational purpose, also being able to assemble it into a manner that is assemblable, you just run into a lot of issues there as a general problem. So it's any kind of integration effort there is fraught with issues that come up. And then similarly, when we apply software to the systems for the first time and then integrates the mission systems, the operations with the vehicle, we expect and we plan for all these issues to come up, and we conduct a lot of tests to show that once we get through all the issues, that the vehicle and the whole system as a whole will perform as we expect at the end.
And after you guys complete the rover, there's going to be a series of environmental testing, right?
Yeah, we have a number of different environmental tests. So we go through vibration tests, where we put the whole rover on top of a vibration table and simulate a kind of launch environment. So we shake it and make sure it doesn't fall apart. We have the thermal vacuum tests, where we put it inside a thermal vacuum chamber. So we bring this huge chamber down to vacuum, and then we cycle the whole vehicle through the thermal profile that we'll see through the mission. And so we'll test there that it can both survive vacuum, and that the heat that we see on the vehicle will be able to survive those. We also have a number of integrated tests where we run through all of our operational products in a flight-like way on the vehicle. So we run through all the activities that we're going to do on the vehicle and make sure that that all works together. And we test with the DSN station as well. So the main thing here is we want comm. If we don't have comm, we don't have anything. So we test with the DSN and to make sure that we get a link through there. And so there's a lot of environmental and system level testing that goes on.
Absolutely. And how do we command? You just talked a little bit about how we're communicating, so how do we command the rover? Is this just like a button that you're pressing, like playing a computer game, or is it a lot more complicated?
I can talk a little bit about the overall commanding, and then you talk about driving.
Yeah, I think that's a better way to do it.
So we have a few different consoles that will command the vehicle. So we have the drivers who are responsible for actually moving the vehicle along. We have the command operators. So the command operators are responsible for maintaining the state of the vehicle. So if there are things going wrong, they're sending up the commands to correct them. If we need to change state for some reason, they'll be the ones that command that. So they kind of they command the state of the vehicle. And then, of course, we have the science instruments. We're going here for exploration. So the science operators will be commanding their own instruments. So the command role actually turns on their instruments, and then once they're on, they're ready to go. Then they start operating and running their commands through the vehicle to their instruments and getting all that data down, understanding what's going on, and just going through these cycles there as well. So there's a few different commanding roles that happen while we're roving around, and then the driving command.
Yeah, so the driving is done a little bit differently than a lot of the way the rest of the rover is being commanded, because we actually work through a tool that DW, who was just on, it was one of the main developers on, and she and in that tool, what we do is that we have the situational awareness coming in from the cameras, from the hazard maps, and from whatever else that, whatever other information is being brought to us down from the flight command structure. And what we do, and this one actually ends up being a little bit more like a video game, because we have this 3D representation of the environment we're in, and it's actually being filled in, a little more details are being filled in by the map scanning that the cameras are capable of doing. And then you make an assessment, and you have this little puck that you put down and say, "Yep, drive there."
And then it does it on the moon.
Yeah.
Yeah.
There's another question here. Does it have any other power source other than solar energy?
Just the solar panels. That's our power source, and that's one of the big constraints that governs a lot of what we do on the mission, not just where we can go with the communications and sun shadows that we were talking about before, but also how we drive. So we always want to keep the aft corners on those back corners that you can see in the live feed there toward the sun. So that's our max power generation angle, and that imposes a nice constraint on the drivers to have to worry about that and all the terrain hazards that are in front of them, and all of the constraints about getting the right kind of science. And so, it's solar power.
Very cool. A question here, how will the rover keep the regolith out of the motors and wheels?
That's a really great question, and it's one of the bigger design challenges that we've had.
Okay.
And another reason, actually, why this looks so different than other rovers that you may have seen. So most of it's not installed, but you can actually kind of see how it looks on the top with the mast. We use the MLI, or multi-layered insulation. That's kind of like these blanket-looking things that are covering a lot of the top of the rover. It's covering the chimney cap you see, and the mast and antenna itself. We use those to cover up sensitive mechanisms and put seals around it to make sure that the dust doesn't really get in there. So unfortunately, right now at the bottom you're seeing bare mechanisms, but that's actually going to be covered up, similar to how the top is. And actually, if people are more interested, they could actually look up some of the previous testing we've done at the Slope Lab, which is at Glenn Research Center.
Right.
That was done with the McGrew unit that I mentioned earlier. We actually had some of those socks and MLI blankets installed So you could actually, and that's actually one of the many tests we were doing there, seeing how well, as we drove through different dirt environments, how does it get in, how well does it reject it, and making sure that it operates well with the mobility system. So like it doesn't create, we don't create pinch points when we try to move. There's a lot of things you have to think about.
Absolutely.
Here, one viewer is saying, where will the rover land? I know it's the South Pole, but maybe you can talk about the Mons Mouton area, the terrain there. Yeah,
kind of the Belay area is about a 5 kilometer by 5 kilometer region, and the landing site itself is picked for a number of constraints. So we want to be towards the South Pole region. We need to be landing in a location that is within our slope limit, so that we can actually drive this vehicle around. The area that we want to go to needs to be of science value, and which can oftentimes be a tricky combination where we want these giant permanently shattered regions, but we also want to be able to traverse and get to those regions, and so that constrains the problem further. So we'll land it around this region in the South Pole, and that's the kind of constraining parts to get to that landing location.
All right. We also have a question about the environment there. I mean, given the high daytime temperatures, how do you manage to keep all these electronics cool? I imagine that's another challenge.
Yeah, so I mentioned this a little earlier. I guess I'll just mention it. That white top that you see is our radiator, and inside there's a box that you could see it in the thumbnail for this stream. Actually, unfortunately, it's covered now, and that's where all the electronics are. And there's a series of heat pipes that are going to be bringing up the heat from those electronics into this radiator, and this radiator is going to be rejecting all that heat into space through way of radiation.
Very efficient. Also, we got a comment, the ramblings are answering more questions. So ramble more was the feedback from the chat. Thank you so much. Really good feedback. We are getting near to the end of our stream, but we do have a couple more questions for you. One is, do you have any advice for people who might want to work on something like this? How did you end up working on NASA's first robotic moon rover?
I'll let you go first.
So how did I get here, and what advice? So I studied mechanical engineering at school, and then I moved pretty quickly after mechanical into control systems engineering, and then into systems engineering, so cool. And then kind of stayed with the systems engineering side of things. It tended to fit better with the things that I like to do. And I think once you get a taste for the flight projects, I started on much smaller flight projects, and once you get a taste, it just keeps going. You just want to keep doing these things. And so it's kind of, once you get the first taste, there's a feedback loop. There's a lot of opportunities at universities to get involved with those spaceflight projects. A lot of smaller missions that are conducted there. That's kind of gets you a shoe in, and then once you have that kind of experience, then you can move on. You get that on your resume and that kind of experience to move forward with. But yeah, what was your?
Yeah, so mine's going to be more of a shameless plug for the internship program at NASA.
We love the internship program.
Yeah, so that's how I got involved. I applied to the internship program. So there's actually two at NASA. One that one, I think we just called it the internship program, where you go in and do an internship and then it's done. But and that is a very valuable program, and that's where a lot of to get a lot of college students involved in NASA, because when you apply and become an intern, you actually are working as a NASA engineer. You actually are doing the real things, and that experience really matters. And then the second internship program that I was mentioning is, and this is going to be the really important one to those who really want to work here. That's the NASA Co-op Pathways program. So if this is this is the way to work at NASA. So what it is that it's an internship, it's a co-op program where you work at NASA for a semester, then you go back to school for a semester and repeat that process until you graduate. And depending on your performance, you will be given a job at NASA. And that's the way.
So that's what happened for you.
Yes, that's what I, yeah. So first I
Success story.
yeah. So first I did the internship program, and that got enough experience on my resume that I was able to I was picked up for the Pathways program. After a few times getting rejected too. But
Awesome
Perseverance,
advice.
yeah.
And I guess the final question here is like, what do you enjoy most about your job?
Right now, for me, we're in this sprint cycle where we're focused on these things called mini sims, and so we have we're pretty. We're getting close towards the end of our software development, so we have quite an integrated software system in a simulation environment. And we get a lot of the team together for the different positions, and we run through the different operational concepts and actually test out these, what we've been building for years now, about how to drive into a PSR, how do we actually drill, how do we perform these operations. And so that's quite fun at the moment, these sprint cycles where we get to integrate it all together and run through it, and just, yeah, it's very exciting.
That's exciting. How about yourself?
definitely the challenges that you're given. I mean, I don't know. For the start, just knowing that I'm working on like one of the coolest robots ever, and yeah, and also being told I get to drive it. Just want to drive it.
Soon. It's happening soon.
Oh yeah.
All right. Thank you so much to everyone who sent us questions today and joined us virtually. And thank you, of course, to our incredible experts, our VIPER mission team members. We so appreciate your time. Thank you for telling us more about the mission and, of course, for answering these questions.
And to learn more about the VIPER mission and get the latest updates, follow at NASA Ames. And we'll see you next time. Go VIPER.
Go VIPER.